Welcome to AI Paperslop. If you are an ML engineer or, an AI researcher trying to keep up with the bleeding edge, you are in the right place.
Absolutely.
We are skipping the pleasantries today. We are jumping straight into a paper that, honestly, completely redefines inference-time compute.
It really does. It's wild.
The paper is called Training Free Loop Transformers. It's by Lizeng Shen, Jonathan Lee, and their team at UT Austin.
Great team.
Yeah. So here is the core insight for you right up front. You can take a frozen, off-the-shelf LLM checkpoint like Qwen 3, Llama 3.2, or even DeepSeek V2 Lite.
Right, the big ones.
Exactly. You pick a narrow band of middle layers and you just loop them at inference time.
And the results are kind of staggering.
They are. Doing this gains you a massive 2 to 2.6 percentage points on incredibly hard reasoning benchmarks like MMLU Pro and GPQA.
Which is huge for a zero-shot intervention.
Right. And you get this with zero weight updates, zero fine-tuning, and zero architectural changes.
Yeah, the mechanism driving this is what makes it so compelling.
Because usually looping is a terrible idea,
right? Historically, it's a disaster. If you just naively repeat layers in a transformer that wasn't explicitly trained for it, the model's performance utterly collapses.
It just outputs garbage.
Exactly. But what the authors realize is that you can't just blindly repeat the layers. You have to treat the loop as this finer-grained substepping...
Substepping of what?
Of the network's inherent residual ordinary differential equation, or ODE.
Okay, wait. Let's unpack this.
Sure.
Because framing a transformer block as a differential equation is a pretty dense concept for a Tuesday morning.
It is a bit math-heavy, yeah.
I've always thought of residual connections as just a way to solve the vanishing gradient problem.
Yeah.
You take the input x and add the output of the attention block, so x plus f of x.
Right, the classic ResNet trick.
Yeah. So how do we get from basic residual addition to, time integration?
Well, the math actually lines up perfectly if you view the layer index as time. That operation, taking your current state and adding the rate of change to it, is mathematically identical to a single forward Euler step on a residual ODE.
Assuming a specific step size, I imagine.
Exactly. Assuming a time step size of h equals 1.
Got it.
The crucial insight from the paper is that the unmodified network, through its massive pre-training run, is fundamentally trained to reach a specific endpoint at the end of that block.
Like destination.
Right. It's aiming for t equals 1. The layers downstream of this block have their weights tuned to accept a feature distribution that looks exactly like it belongs at that t equals 1 state.
So if we look at previous failed attempts to loop a model at inference time, they were basically treating it like walking.
That's a good analogy, yeah.
Let's say your destination is exactly 1 block away. The standard network takes one giant step of h equals 1 and arrives at t equals 1.
Perfect.
But if you just repeat that block k times, say looping it 4 times, you are taking 4 giant steps of h equals 1.
And you walk right past the destination.
Right. You walk past the neighborhood entirely and end up at t equals 4.
Exactly.
The later layers are sitting there waiting for an input from t equals 1, and you hand them a hidden state from t equals 4.
Yeah.
To them, it's just out of distribution noise.
The paper's data demonstrates that catastrophic collapse incredibly clearly.
What do the numbers look like?
So when they tested naive looping at k equals 4 on the Qwen 3 0.6b instruct model, the Lambertata perplexity just exploded.
How bad?
It went from a baseline of 13 to over 1054.
Oh, wow.
Over 1,000. Yeah, the network completely loses the thread of the text. It's cooked.
So how do they fix it?
The solution isn't to advance your integration timeout to t equals k. Instead, you use smaller, damped substeps.
Meaning you shrank the step size.
Right. If you want to take k steps through the loop, you use a step size of h equals 1 over k.
Ah, okay. So if I'm looping 4 times, my step size is 0.25.
Exactly. You are still aiming for that exact same destination, t equals 1, but by taking smaller steps, you arrive at a much more refined, highly accurate approximation of that state.
I follow the logic of needing finer substeps. But looking at their ablation studies, I got a bit lost on the math they actually deployed to do this.
It gets pretty deep into numerical methods.
Because if hitting t equals 1 is just an ODE fixed point problem, why aren't they throwing the absolute heaviest state-of-the-art numerical integration solvers at this?
You'd think that would work, right?
Yeah. I saw they tested Anderson acceleration, which is, designed specifically to optimize these kinds of trajectories, and it somehow made the model significantly worse.
It's honestly the most counterintuitive finding in the paper.
Really?
Yeah. They ran these extensive ablation studies on Qwen3 1.7b,
Yeah.
and those advanced fixed-point accelerators failed spectacularly.
How spectacularly were we talking?
Applying Anderson acceleration at k equals 8 didn't just underperform. It dropped the model's accuracy by a massive 18 percentage points.
Wait, minus 18 points.
Minus 18.
How does a highly sophisticated solver fail that badly on a simple trajectory refinement?
Well, the failure of Anderson acceleration tells us something profound about the latent space inside these LLMs.
Which is what?
Anderson assumes that the underlying vector field is a true contractive map.
Okay, so it assumes the space is smooth.
Exactly. It assumes the sequence of hidden states is approaching a fixed point in a smooth, highly exploitable way. But the middle of a pre-trained transformer block is incredibly noisy.
It's not a clean mathematical curve.
No, it is not a perfectly smooth, continuous ODE.
So when Anderson tries to speed things up,
When it looks at the history of the gradients and tries to extrapolate the fastest path to the destination, it overshoots wildly.
so it's kind of like trying to use a GPS system that expects you to walk in a perfectly straight line to your destination,
Sure.
but you're actually navigating this complex, winding maze.
Mm-hmm.
The GPS looks at your last 3 steps, extrapolates your path, assuming the world is flat and open, overcorrects, and routes you right into a brick wall.
That maps perfectly to the mechanism, actually. The latent space is just too complex for aggressive extrapolation.
Which leads us to the winning recipe they finally landed on.
Right. Across 45 different combinations of models and benchmarks, the only method that robustly worked without requiring per-cell hyperparameter tuning was a k-stage explicit Runge-Kutta integrator.
Runge-Kutta.
Yes, specifically a k equals 2 or k equals 3 stage Runge-Kutta. It interpolates between the base output and the damped Euler updates.
So for the engineers listening who are trying to picture this, what does that k-stage Runge-Kutta actually look like in code?
Essentially, instead of taking a blind step based purely on your current position, Runge-Kutta computes intermediate slopes.
Like scouting ahead.
Exactly. It takes a tentative fraction of a step, evaluates the slope or the output of the transformer layer at that midpoint, and then uses that information to take a much more accurate full step.
I see.
It's gentle enough to refine the state without making those overly aggressive assumptions about the smoothness of the latent space that doomed the Anderson method.
Okay, so the Runge-Kutta solver works beautifully for dense models. But the landscape of top-tier models you mentioned up front, like Llama 3.2, DeepSeek, those aren't dense transformers.
No, they are a mixture of experts.
Right. They rely on sparse routing. And applying this Runge-Kutta math directly to a MOE backbone apparently breaks them.
It causes a severe degradation, yeah.
Why is that?
To understand why, we have to look at the architecture of the standard loop, which operates in what they call block mode.
Block mode.
Right. In block mode, you take a contiguous chunk of layers, let's say layers 15 through 18. You run the hidden state through that entire 4-layer block, and then you loop it back to the start of layer 15.
Okay.
In a dense model, that's fine. But in a MOE model, every single layer contains a router.
The gating network.
Exactly. A gating network that calculates a softmax distribution to decide which specific experts the token should be sent to.
I can see the cascade failure happening here.
It's pretty messy.
If we loop a whole block of MOE layers, the gating network at layer 15 is going to see slightly shifted hidden states on every single pass because our ODE solver is continuously refining that state.
Yes. The authors diagnosed this exact issue and termed it routing thrash.
Routing thrash? That sounds expensive.
It is. A tiny shift in the hidden state on iteration 2 changes the softmax distribution just enough that the top 2 experts shift.
Oh, I see.
The router at layer 15 suddenly sends the token to a completely different set of experts than it did on iteration 1.
Which means the math being applied is completely different.
Exactly. And because you are looping through multiple layers, these small routing perturbations compound exponentially across the block.
It's chaos.
Total chaos. The noise of suddenly switching expert weights completely destroys the intended ODE refinement.
It's kind of like an automated package delivery system.
How so?
The sorting machine routes packages based on weight. On the first pass, a package weighs 1.0 pounds, so it goes to warehouse A. On the loop back, our Runge-Kutta math refined the package, so it now weighs 1.01 pounds. The router reads the new weight, flags it, and suddenly sends it to warehouse B.
Yes, exactly.
You're completely changing the processing pipeline instead of refining the destination. So how do we fix routing thrash without, retraining the router?
The authors engineered this brilliant structural workaround called layer mode iteration.
Layer mode.
Yes. Instead of iterating the whole block as one giant unit, where the state travels from 15 to 18 and back, you iterate each individual layer k times before moving on to the next one.
Oh, wow.
So you run layer 15k times, then you run layer 16k times.
That makes so much sense.
It's very elegant.
Because if you iterate entirely within the boundary of a single MOE layer, you can just pin the expert routing in place.
Precisely. You compute the gating decision once on the very first pass, find out it needs warehouse A, and then you force the network to apply that exact same expert mixture for all subsequent k iterations within that layer.
The stabilization must be immediate.
It really is. By eliminating the routing noise, the hidden state follows the intended ODE trajectory perfectly.
Did it fix the MOE performance?
It did. Switching from block mode to layer mode on MOE backbones flipped models from negative performance regressions to solid positive gains.
That's awesome.
Yeah. On the hard MOE benchmarks for Qwen 1.5 MOE and Moonlight 16B, pinning the routing with layer mode yielded up to a plus 1.7 percentage point increase.
So if you are touching in MODI checkpoint, layer mode is just mandatory.
Absolutely mandatory.
Okay, so let's put ourselves in the shoes of someone trying to code this up for a project tonight.
Sure.
We have the Runge-Kutta math. We know to use block mode for dense models and layer mode for MOEs. But a model like Llama has dozens of layers. Where do we actually put the loop?
The authors formalize this into something they call the depth fraction rule.
Depth fraction rule.
Right. Across the 9 different architectures they tested, the optimal loop window sits in a very narrow band right in the middle of the network.
The middle, not the beginning.
No, specifically between a depth fraction of 0.45 and 0.60.
So if I have like a 32-layer model, we're talking about grabbing layers 14 through 18 right in the belly of the network.
Exactly.
Why that specific window?
It comes down to what different stages of a transformer are actually doing.
Okay.
You avoid the early layers because they're heavily focused on basic lexical processing and feature extraction.
Right. Just figuring out what the words are.
Exactly.
Yeah.
And you strictly avoid the late layers because they act as highly specialized output heads, projecting the latent state back into the vocabulary space.
So the middle is the sweet spot.
The middle layers are where the dense, abstract, conceptual reasoning happens. It's also where the network has the most redundant capacity, making it the most amenable to continuous refinement.
That makes intuitive sense, actually.
Yeah.
You give the model extra time to think while it's wrestling with the logic, not while it's just parsing grammar or, picking the final word.
Precisely.
But let's talk about the real engineering headache here, the KV cache.
Ah, yes, the KV cache.
If I'm using Hugging Face's standard dynamic cache, it unconditionally appends new keys and values every time a token passes through a layer.
It does.
So if I run a 4-layer block 3 times, my sequence length just virtually exploded, didn't it? Doesn't the attention mechanism suddenly see 3 copies of the prompt?
It does. And if left unchecked, it causes massive memory bloat.
I can imagine.
Worse, it destroys the attention matrix because the model starts heavily attending to redundant intermediate scratchpad tokens.
So how do you solve that?
To solve this, the authors implemented a snapshot and restore algorithm for the decode phase.
Snapshot and restore.
Right. During the loop itself, you absolutely want the model to attend to the past context to keep its reasoning grounded. So you must run the loop body with the use cache equals true flag.
Right. The model needs to read the context to do its math. But how do we stop it from saving its rough drafts to the cache?
You snapshot the lengths of the cache before the loop begins.
No.
Then, immediately after each iteration of the loop, you manually crop the key and value tensors back to that original length.
Oh, that's clever.
You are essentially letting the model use the cache as a temporary scratchpad and then wiping the scratchpad clean after every single step.
Okay, so we wipe the scratchpad so the cache doesn't blow up.
Yeah.
But the downstream layers, the ones after our loop block, they still need something in the cache to function, right?
They do.
You have to write a final version of the key and value states.
Yes. That is handled by a single stash pass after the loop fully finishes.
A stash pass.
But this introduces a fascinating problem. What specific state do you stash for the downstream layers?
Right, because you have the original state and the new refined state?
Exactly. The authors tested various strategies and found 2 distinct winners depending on the task.
What are they?
First is cache equals first, which stashes the hidden state from before the loop even started. This completely dominates when you're running long chain of thought prompts.
Wait, really?
Yeah. But cache equals last, which stashes the post loop, highly refined state, performs significantly better for short, structured outputs like pure math equations or code generation.
I really want to dig into the why there.
It's super interesting.
Because why would a long chain of thought prompt benefit from stashing the unrefined pre-loop state? Shouldn't we want to pass forward the smartest, most refined version of the thought?
You'd think so, but it has to do with trajectory anchoring.
Trajectory anchor.
Yeah. Chain of thought requires the model to maintain a coherent narrative across hundreds of generated tokens.
Right.
The pre-loop state contains the unmodified, highly stable context of the original prompt. If you stash the refined state for a long generation task, small numerical drifts in the KV cache can compound over hundreds of tokens.
Causing the model to drift off topic.
Exactly. It causes the model to lose the original premise.
Wow.
Short tasks, on the other hand, like outputting a Python function or a final math answer, don't suffer from that long horizon drift.
Because they're over quickly.
Right, so they benefit immensely from the highly concentrated, refined logic of the cache equals last state.
And what happens if we try to bypass the stash pass entirely? Like, what if we just use cache equals none?
Oh, the generation completely collapses.
Just totally breaks.
Yeah. The downstream layers expect a coherent history of keys and values to attend to. If you feed them nothing, the attention mechanism breaks down and outputs gibberish.
Okay, so we've gone deep into the Runge-Kutta ODEs, pinning the MOE routers and cropping the KV cache.
We've covered a lot of ground.
Now we need to look at this from a production standpoint. Because the ultimate test for any ML practitioner tuning into a deep dive on AI paper slop is, is this actually worth the compute overhead to deploy?
That's the million-dollar question.
Literally.
Well, the compute spent validating this was massive, about 20,000 H100 hours.
Wow.
And the headline gains definitely justify the attention. We're looking at plus 2.6, 4 percentage points on MMLU Pro for Qwen 3.4b instruct.
That's massive for a 4B model.
And plus 2.30 points on the ARC challenge for Qwen 1.5 MOE. The loop basically acts as a few-shot invariant frozen context refiner.
It flat out makes the model smarter at test time.
Particularly on knowledge-heavy reasoning tasks.
But nothing in machine learning is truly free.
Definitely not.
Extra forward passes mean extra math, which means extra latency. If I'm footing the bill for cloud GPUs, what is the wall clock penalty for running this full decode loop at k equals 3?
If you run the loop on every single generated token, what they call a full decode loop, it incurs about a 22% wall clock slowdown.
22% is chunky.
It is.
If you're building a real-time consumer-facing chatbot, that kind of latency spike might be a deal breaker.
For sure.
I mean, for offline batch processing, sure, people will take that trade for a 2.6-point bump.
Mm-hmm.
But for interactive apps, that hurts.
It does, which is why the paper provides a massive deployment workaround. They call it bypass mode.
Bypass mode, how does that work?
You apply the Runge-Kutta loop only during the prefill phase.
The prompt processing part.
Exactly. That means you loop the continuous latent state only when the model is reading the initial prompt.
Yep. Okay.
Once the model transitions into the autoregressive token generation phase, spitting out the answer token by token, you skip the loop entirely.
You just go back to normal.
Right. You just run standard single pass forward propagation.
Wait, if you skip the loop during generation, do you still get the performance bump?
You do.
And what does that do to the latency?
Well, you retain the vast majority of the reasoning performance bump. And in their profiling, it actually resulted in a 1.5% speed up compared to the standard unlooped baseline.
Wait. A speed up?
A speed up.
How is doing more math during the prefill phase resulting in a faster overall response time than the baseline? That sounds like magic.
It's not magic. It just comes down to memory bandwidth constraints.
Okay, break that down for me.
Writing KV states during token-by-token generation is heavily memory-bound. By isolating the heavy ODE looping to the prefill phase, where matrix multiplications are highly parallelized and compute-bound, you build this deeply refined internal representation of the prompt.
Right, you front-load the heavy lifting.
Exactly. Then, during generation, the model has a slightly leaner KV write path because you aren't managing all those complex scratchpad states.
Oh, I see.
You just coast on the standard, highly optimized fast path. You get a smarter context representation for literally less than zero overhead at inference time.
That is an incredible engineering trick.
It's very smart.
Because the hard work of understanding a complex reasoning question happens when reading the prompt. You let the loop cook on the prompt token,
And then you just reap the benefits during generation.
it really proves that test-time compute doesn't just have to mean generating long chains of thought.
No, not at all.
You can spend compute internally, right in the continuous latent space, before a single output token is ever generated.
Exactly. It shows that latent reasoning can be manipulated directly through the geometry of the network.
Which perfectly wraps up our core takeaway for today.
I'd say so.
We don't always need massive reinforcement learning from human feedback runs or, complex, continuous latent space training recipes to squeeze blood from a stone.
Right.
Sometimes you just need to look at your transformer, identify the implicit math, and treat it like the differential equation it actually is.
And that leaves us with a final provocative thought to mull over, actually.
Oh, what's that?
We saw today that treating a frozen model as an ODE yields significant reasoning power, right?
Yeah.
But we also saw that classical fixed-point accelerators like Anderson failed because the middle layers aren't perfectly contractive. They are noisy.
Right, the latent space maze.
So what happens if pre-training recipes actively start enforcing those contractive properties?
Oh, wow.
Could future LLMs be explicitly designed so that those failed accelerators suddenly work?
If they smoothed out the maze?
Exactly. If so, we might unlock massive, dynamically scalable reasoning depth at inference time just by turning a mathematical key.
A base model explicitly built from day one to be looped by an external solver.
It's entirely possible.
That is a wild thought to end on. Thanks for joining us for this deep dive on AI paper slop, and we'll see you next time.